All right, so today's review is going to be on static electricity. So first off, we know that the charge is always transferred with electrons. So we have this electron, and it is what gives rise to the charge difference between two objects. So I have this electron, and it has a charge of -1 elementary charge, which we have minus 1.60 times 10 to the minus 19 coulombs. Okay, so that's the charge on the electron. So how does one gain or lose charge? Well, if you want to make something positive, you need to strip away the electrons from it, and if you want to make something negative, you have to add the electrons to it. Okay, so that's just some basic overview. But if we compare what the charge distribution looks like on an insulator, if I throw a bunch of negative charges on an insulator, the basis of it being an insulator means that the charges are not easily moved around. So as long as there is not a significant amount of charge, maybe there'll be a slight movement of these electrons, but the general, basically, wherever I put the electrons on the insulator, it will stay in that location. Now the net charge is still negative, but they're not equally distributed. Unlike in a conductor, if you throw those bunch of negative charges, let's say I place them right here, well, on a conductor, those electrons are free to move. So since they all repel each other, what they'll do is they'll move into the outer surface. Okay, so they're going to have this nice equal distribution around that conductor at some time later, some short time later. So if we look at the electric field inside of that conductor, if you consider the electrons' movement, they're going to move such that they're kind of this nice, equally spaced distribution. And since we know that the electric field gives rise to an electric force, that if I think of the electric field inside, right, sometime later we said that the electrons don't move. And if they don't move, then that means that the F net is 0 on those electrons. And if the F net is 0, then the electric field inside of that object is 0. And so what we end up seeing is that since the charges move around initially, sometime later, some short time later, the electric field on a conductor inside of it is going to be 0. Now we also talked about electric potential, which electric potential is defined as the energy something has per unit charge, so the electrical energy per unit charge. And so what we talked about it initially was with these parallel plates. So the nice thing about two parallel plates is that the electric field inside of the parallel plates is nice and uniform. And so here's a nice connection between some kinematics and also some electricity. So if I place an electron right here, and I place an electron right here, since they have the same electric field on them, even though the charge number 1 is closer to the positive plate than charge number 2, it is going to experience the same force because it will have the same E. They both have the same charge, so therefore they have the same force. Now, however, it doesn't mean that both of those electrons have the same amount of energy on them, okay, or energy stored within them. Now, to answer the question, we know that the potential difference between two places is equal to the amount of energy that something has per unit charge, okay, and that's basically what we have here. And that you have to ask yourself the question, where does the electron want to be? Meaning that if I let go of both of these, where will they naturally fall? Well, the electron 1, since the electron 1 is close to the parallel plate, that means that what it is in its least energetic state. An electron 2, since it is further away, there's some distance in between those two plates, then it's going to be at a higher energy. Therefore, it's going to be at a higher voltage. So let's say 3 volts, whatever that number is. And then this is at 0 volts. So maybe if I bring it all the way close, if I push this all the way down towards the positive plate, if I bring it an extra, few meters here, a few centimeters, then it might be at a higher voltage, let's say 6 volts. And so the interesting about this is that if you take that electron, and let's say you force it over to that parallel plate, you've now put some electrical potential energy into it. And that electrical potential energy would be equal to the potential difference between where it's located, so in this case 6 volts, and where it's going to head, 0 volts, times the charge. So if I express this would be easier to express in electron volt. We have 6 volts times 1 elementary charge. I have 6 eV worth of energy. Now, what's nice about this is that the change in electrical potential energy will be equal to the change in kinetic energy. So I could expect it to have 6 eV worth of kinetic energy when it hits that positive plate. So you can do a nice conservation of energy for the electrons between these parallel plates. And once again, the reason why this works out really nicely is that the electric field is constant. Now, for a positive charge, the electric field, as we know, is going outward in all directions, radially outward, because the electric fields are drawn based on which way a positive charge will move. And the electric field value is kq over r squared. So there's an inverse relationship. But we also know that the electric potential from a point source is kq over r. So let's say I knew the electric potential for a positive, well, actually, let's do a negative charge. So let's place an electron right here, because the electron, when it's closest to it, let's say it's right on that surface, is at 0 volts. But if I go some distance away, let's say I go 1 centimeter away, then I can calculate what the electric potential is. So let's say it works out to be, 1 volt. But what's interesting about that is if I go 1 centimeter away this way, I get 1 volt. And then 1 centimeter this way, I get 1 volt. And so I get basically everywhere around here that's 1 centimeter away from the center, or from the surface, ends up being at that 1 volt. Now this line right here is a line that has equal potential. So that's why we call it a equipotential line. And you could think of it as if you take that electron and you move it around anywhere along there, it's going to have the same amount of energy, meaning that it does not take any work to move it from position 1 to position 2, because it doesn't have any more energy, or it didn't lose any energy. So therefore, we didn't have to do any work to that to move there. All right, so let's talk a little bit more about the potential. Let's talk about the potential on a conductor. So let's say I have a conducting sphere, once again, and I put some charge on it, and they move around and become equally distributed around, and I wanted to calculate the potential inside. So what's going on with the potential inside? Well, so you have to ask yourself, why does charge move in the first place? And the answer to that question is that there is a potential difference. But remember, we said that the E field inside the conductor is equal to 0. And the E field is what gives rise to a force. And if the electric field is 0, then the force is 0, then what we could say is that the charges are not moving. So that means that our potential difference, not our potential, but our potential difference is 0. So that means that the potential is constant. It might be 10 volts, but it's 10 volts right here, and it's, if I move from left to right, even if it's diagonally, then it's 10 volts here. So the difference in this case is 0. So I can calculate what that potential is by the kq over r, and the r would be the radius of that, because it'd be from the center to the outside. But that number from moving from anywhere along that radius would be the same. And so what's interesting is if we make a plot of potential as a function of distance from center, so 0 meters being the center of that sphere. If I move to the left, let's say some distance r, and I move to the right some distance r, so meaning that from here to here represents the distance, the diameter of the circle, it's going to be at a constant potential. Once again, because the electric field is 0. But then beyond that, from the surface down, it's going to fade in a inverse fashion, since V is proportional to 1 over R. And it's going to do the same thing on the other side. Okay, so we have a nice inverse relationship there. Now, I started to kind of give mention to the fact that we could also introduce some kinematic stuff when we are dealing with parallel plates. So if I take an electron and I give it some horizontal velocity, well, the field goes down, but we know that negative charges are attracted to positive things. So when this electron enters this field sometime later, it is going to have an electric force up. So it's got a velocity that is going to the right in this diagram, it's got a force that's going up, and that direction of that force always is up. It doesn't change as it starts bending. And so what we could see is that this electron is going to take a parabolic path within the plate. And let's say, for example, it does make it outside of the plate without hitting the positive plate. Well, then at that point, it's going to go off on a tangent to the position where it is at that point and go straight. So it's still going to have that same velocity it entered with, the Vx. It's now going to be introduced to some Vy, and the resulting velocity would be the vector sum of those two components. Okay, so we could talk about the acceleration, we could talk about how far it traveled, what is its vertical distance, so what is that delta y, using some kinematics equations. So that's all I have on static electricity. There's obviously a variety of things that I left out, but these are what I feel are the most important things. Thanks for watching. Have a good night. Bye-bye.